Hello, everyone. Welcome to the next hour or so of Flip. So we're going to be taking a look at a whole bunch of things regarding flip fluids, flip simulations, and also looking at some whitewater, some approaches to doing whitewater. And in typical fashion, you're always generating cache files, and that's actually what I'm doing right now, rendering some cache files for a particular shot that I'm working on, so we can actually do some whitewater. So the first area that I want to take a look at, a lot of requests about flip fluids in general, and getting more comfortable with flip fluids themselves is a big task. So the first exercise that I want to get looking at is this idea about taking a flip simulation and being able to modify it in various different ways. In this particular example that we'll be working up from scratch, because a lot of you have also asked to see some flip simulations being done from scratch. And what I'm going to do is I'm actually going to bail out. I think I've cached enough files over this. I'm going to kill that. And let's save this session. We'll be looking at the river a little bit later when we're dealing with whitewater. So it's a really simple, so I get some performance back, that is. So this is a really simple scene where I have a water emitter going down a waterfall with some collision objects. And we'll take a look, first of all, as to how to create a first-class collider, and then how to create nice emitters, and then different ways to modify your flip sim. And I'm working with a fairly low resolution sim so we can get some reasonable time and feedback, which is what we want to do when we start playing around, peering into the various data types that are available to us in the various simulation objects inside of Flip. So I'll just show you, this is what we're going to be working on for the next little while, is getting comfortable with getting right inside of Flip. A lot of techniques that you see online on OddForce and on the forums, and even with the other flip style technology, you're basically driving into the points themselves. There are a couple options where they do, briefly investigate looking at the actual volumes themselves when we're dealing with flip. But in this particular exercise, what I'm doing is I'm injecting, I'm taking a flip object, and with a gas field bop, I'm able to actually do a lot of really, really cool stuff. Injecting curl noise, for instance. That was one of the first questions, is how do you take a flip sim and how do you add basic curl noise into your simulation? So we'll be taking a look at the various fields that we can peel off. And in this case, I'm using the surface field, for instance, and also changing some of the density of the fluid, just to break the fluid up a bit and to inject some air let me go up here again. About 13. There we go. So basically, just trying to inject some life into the flip fluid without actually working on the particles themselves, but working on the flip fluid directly. So I'm going to leave this file up just in case I lose my way, which is more than likely as we take a look at this. Believe it or not, this is just a file that I created a couple days ago. One of the exercises was the question, how can you simulate some pseudo air inside of a flip simulation using Houdini 15.5 modern techniques? And invariably, I go straight to the fields. And as we know, with a flip fluid, the particle separation for the particles determines the particle density. But the grid scale is at twice the size of the particle separation, which means if we're able to work on the grids and get the results that we want, we're actually way ahead of the game because we're processing much less data than if you're just processing the particles in turn. And volumes give us a couple extra options not available on the particles themselves. And because the flip solver itself, the core algorithm, is actually working on volumes, why not go inside the volumes and do that as well? So the first thing we want to do is inject some noise into the flip sim. So I've got a file here that we're going to start off with And I said I would start off with a new file. So I'm using a Mac. I like shells. So I always have to say that I like shells. You don't have to use shells. You can double click on files. God is laughing. It's not, well, it's a goal. If you were not using shells, it's a goal. And just use shells. So I have a very basic start scene, and it's just a basic terrain that I modeled together. You can generate terrains however you want. I was really tempted to use the next release because we got some amazing tools that creates far more interesting data than this. But this makes for a decent piece of test geometry where I just have I have a little bit of geometry up here where I want to put my emitter and sort of break the water up. And I just use simple techniques where I just basically took a curve, extruded it, modified it a bit, and then I used an extrude volume SOP, and I cheated by changing the base normal just so I could get away from any madness, because if you do a flat, you might get some odd geometry on the side here. And it doesn't really matter, it's just a collider, right? And then I do a VDB from polygons at enough resolution, and middle mouse on that, sure enough, I got a VD. And then, of course, I sculpt box, I just array it, and then finally convert it into a VDBs as well, and then I use VDB combine. VDB modeling, you should, if you're not familiar with working with volumes to do sculpting and to do booleans and to model geometry, definitely add it to your to-do list because it's a very powerful way of creating some really first-class collision geometry. And then finally, I convert it back to polygons. I do that to make my life easy. I could have actually passed these colliders right into the simulation engine, but in this case, I'm just going to use polygons. It makes the shelf tools a lot easier to use. So I'm going to go up. Now, the first thing I need to do is go to rigid bodies. Well, even last session we talked about if I want to put a collider into flip, I always use the deforming object because it gives you a first-class volume collider, and that's what I'm doing, deforming object. And as we saw before, the one thing I would need to do inside of the dynamics network is go on the actual static object, which is generating the simulation object for me. It's initializing the simulation object for me, and just turn off deforming geometry because it's not deforming. And go up. Now I need to put an emitter, so let's put just a simple box. And now, in this case, I'm just going to make it fairly straightforward. I'm just going to put an emitter up here, call this emitter, dive inside, and simple box handle, escape, enter. Yeah, sometimes even you have to, if you don't see the handles right away when you select the node, just tap the escape key and then the enter key again to refresh the node to get your nice handles. And I just want to create a simple fluid emitter in here. And so a lot of times, there. Now the example file I've provided with you guys in the kit you'll be getting after the seminar, I actually go ahead and model everything from scratch. I didn't even use the shelf tools to do all of that. Unfortunately, I don't know if we have all the time to do that, but we can have a bit of a start at that. But the fluid source is a fantastic tool inside of SOPs for generating all the first-class data. What it does is it has some presets on it. If I go to the container settings under fluid source, and there's source flip. If you choose source flip, it'll initialize all the tabs, giving you the right presets to generate a first-class emitter inside of a flip simulation. In the file I have attached, I actually break the fluid source apart and even build the various pieces that you need. As I said, the fluid source does such a great job of it, and you're basically replicating what it does. But, so I'm now going to go to the velocity volumes, and I want to give this some initial velocity in the z direction, z maybe, and add velocity over, and we can add some initial curl noise. and we can do that that way. I'm going to touch a bit on, you can actually just, we can, just to give you a little bit of an idea of working with volumes, because when we go into docs, we are going to be working with volumes in box. So why don't we spend a couple minutes in here and just play around with the curl noise. I'm going to take the curl noise away here. And by adding velocity, middle mouse in the node, you can see that we created 3 volumes, vel x, vel y, and vel z. So now what I want to do is I want to use a volume VOP. And just to refresh, the volume VOP processes volumetric data using vex functions, vex options. And what we want to do is compute some curl noise for our volume and just animate it. So instead of using the fluid source, we need to get comfortable with working with volumes in these nodes. Middle mouse on fluid source, we're going to be working with names as opposed to index numbers on volumes. So we have a volume called surface and volume called vel x, vel y, and vel z. So in the volume VOP, to work on the velocities, you need to use the bind VOP. So tab bind, and it's all namespace. So if I just put in density in here, I'll be working the density. But then I'll be duplicating what I have up here anyway. So the volume VOP globals actually gives me the density field. What I want is vel. And not vel x, vel y, and vel z, vel dot x. No, you can actually bring them in as a vector. So if you didn't know that, and it's going to be a direction vector because they're velocity direction vectors, just in case I need to give them a hint. And what this does is it's got a direction default. But if the parameter, or if the volume vel is available to me, this will be overridden. And the complement to the bind is the bind export, which is basically the same operator, but it's set up to do an export for you. So again, you're having to type the vel again. Nothing's stopping you from copying and pasting this node and doing the same thing. And that's exactly what I'm going to do. So you can just copy and paste it as well. And you'll get the vel direction. But what you need to worry about here is export. So this one will always do when input is connected. Actually, I did the wrong one. So I'm going to select better. Select this guy. And okay, I see what's happening. So when you copy and paste it, it was a bit of a funk, but we've now redone our selection. So this one does the import, and this one does the export. And there's this option in here. You can see that in the VOP network, when we have 2 parameters or 2 binds that are set to the same variable, only one of them is available for editing. It's just the way VOPs is set up so that the compiler doesn't get confused and the user doesn't get confused. So we actually have this parameter here. We use this node to set parameter attributes, which means this guy now becomes the active one. So now the export is going to be when input is connected. I don't know why I just set into there. That's interesting. Why that one? Okay, it doesn't. That's an interesting one. But anyway, so now I can do whatever I want to the velocity field between these 2 links. So this is the hardest part, actually, knowing that you can, by name, modify any volume that you want. And we can see here in the viewport, we're going to get some interesting updates here. So we can have straight velocity. So we can actually go hit the tab key. And there's the 2 most favorite areas inside of VOPs that I love to go through all the time is noise and patterns. It's kind of neat that they're right next to each other. It's a happenstance accident. But this is where all of the, this is where these 2 right here is how you make proceduralism work in the real world. Everything else is just housekeeping with attributes. But if you want to have a procedural system that looks organic, you're going to be infusing a lot of noise and a lot of patterns and mucking around with it. So we want to use curl noise, which is a very specific type of noise that's periodic, and it's also non-divergent noise, which means that no matter where you evaluate the curl noise field, there will be no pressure gain or pressure loss. In other words, there's no values that are trending anywhere. It's a very even, flat noise that gives you nice, curly, swirly. That's that swirliness that we associate with all fluid simulations. And the position, we're just going to be cheap and wire in P, because that's a good position. You'll notice that we have involves, just to recap, that if you ever see lowercase pause, you need to provide an input. But if you see an uppercase P, which is identical to the global as defined, it's just a hint to tell you that it probably defines P anyway internally, so you don't need to worry about it. But in this case, we do have to do position. And what we can do now is we can add the curl noise. So I'm just putting down a simple add block, drag it on top of there, and then we can add the curl noise onto our velocity. I'm just going to make sure that I have, yes, I do. And the curl noise, position, frequency, amplitude, and I think my binds are good. Val, direction vector, val, direction vector. Yeah, that should be working. Curl noise is type curl noise, frequency. My frequency might be too large, so let's try increasing that. I should be seeing noise in here now. Interesting. Very interesting. So let me go up here and make sure everything's okay. I've got val. Yeah, this should be working. Position is P, the current position I'm doing. I don't know if my binds are, there's some funkiness happening with my binds when I did the val, so I'm going to take this, I'm going to redo my vals. I'm going to put the bind again. I didn't trust that actually. Tag bind and change that to val. I'm going to make that the direction vector. And I'm going to put down another bind export like I did before. And I'm going to put this to val as well. As soon as I do that, they're both changing. That's interesting. So what I'm going to do is I'm just going to blow away the one, and I'm going to drive directly into this one. Still not. We're going to work on this later on. We'll get that to go. But the fluid source should be fine as well. So that should have worked. There's my curl noise. We'll get that to work later. Give me one more try. Curl noise. Bind val. Export. Maybe export always. If you ever get a problem, I'm just going to put down this bind here, and I'm going to see if, oh, that's probably why. Yeah, feedback there. Up. Turn the curl off. And I'm just going to put a constant in there to see if that actually works. 1, 0. No. Yeah, I do use the volume trail on that as well. If you take a look at the other file that I was working on, if I go up here, I actually did this inside of the fluid emitter. In the other one I do actually. So you know what, for this one, I'm just gonna bypass that for now, and we'll get that to work later on. Yeah, sorry about that. But that should be pretty straight. Yeah. Let me just try a different type of noise. Let's try just a good old anti-alias noise. Position, let's do vector in, vector out. See if there's something up with my curl noise. So 3D input, 3D output, and just wire that into the add. That directly in the bind. No idea. I'm just going to go with the fluid source. It's doing the same thing internally. So yeah, so it's doing the same thing internally. It should be fine. But I don't want as much curl noise, so I'm going to scale that back. That's not the whole purpose of what I want to cover anyway. And let's go up. And I'm going to go to the particle fluid shelf tool. And I'm going to turn this into an emitter, a particle emitter. And the tip says if there's a fluid tank, there is no fluid tank, so I'm just going to hit enter again. No surface found. Oh well, let's go inside of here. Let's go up again. Yeah, it didn't work. The odds are against me today. But it added all of the correct nodes, which is really interesting. That is interesting. PDP back, compare PDP, collision source. Oh, I did it on the wrong one, I think. Up here. I should have selected the fluid emitter, I'm sorry. So emit particle fluid. It's better. Right. Fluid source. That's, It's a collision object, my fluid emitter. Yeah, should be fine. And actually, I blew away the wrong stuff from the train as well. I needed all of that. Yeah, that's all good.
So you have a true flow field, not one vector. That's why you're finding it.
Oh, that's why. Okay, I thought I defined the vector.
Thank you, Dimitri.
Okay, so let me go to the fluid emitter again. Volume valve. Bind valve. Direction. Yeah, free flow vector. Let's see if that works. Although the direction vector did work yesterday, so let me just turn off the curl. No, it's something up with my scene.
Something that works, but you have to use the volume trail.
Oh, to visualize it. Oh, shoot, he's right.
Florian Bird.
Yes! Jeez, I'm sorry.
Thanks, Florian.
Of course it does work. My mind's racing a million miles here. So you have to do a volume slice, and then the volume slice, and then you can do a volume trail. And let's wire the slice in for the points, and the trail will be coming from our volumes. And there we go. So we are definitely getting curl noise. It's just me being a boob. And another thing that we have to worry about the volume slice is it's got to work on the attributes, not density. But you can see that we actually have the curl noise. And chances are I've got 3 volumes in here, so I can just blow away under the volume slice. The source group can be set to vel, and just take just vel, or you can slice the density. I'm sorry. And then the volume trail will give you a velocity. And then everything works fine again. So I can go inside of here. Yeah, my brain's not working 100%, so let me put that in the bind. So let's wire that out. And because we're driving the curl noise directly into the velocity, it's not going to do that. So let me put that under the bind. And this thing is just going to be vel. And let's just add. So we're back to where we started off from. Sorry about that, guys. My brain was in DOPS because in DOPS, the volume trail doesn't give you that. So, and the volume up. So that's the fluid source. So being able to work with volumes directly inside of VOPS is really important. But again, visualization is key, right? So now I'm going to put down a null. I'm just going to put down a null up to the fluid source. And that's where I want to hang everything off to. Select my null. Okay, flip. And I should have everything I need in here. Yeah, surface and velocity go up. And my fluid emitter, let's try this again. Make sure that's all safe. That's the trains, get one. Select my fluid emitter, emit particles. It thinks I have a fluid sim, or that's my collider. Oh, this stuff should be flip object, flip solver, and let's do it all from scratch. And we have a fluid source. Just do a source volume. And the source volume goes into the last input of the flip solver, and then we can wire the flip solver into the merge. And then we can actually bring up the contents of our flip solver directly. As we saw with the fluid source in SOPs, in the actual source volume in docs, we can go source flip as well. and it sets everything up for us to do to import the piece of geometry that we need to bring in. And all we need to do is basically put in the volume path, which is going to be out the train. It's not that one, but it's going to be the out to flip. So let me just wire that back in. Enter. Sorry. And let's hide everything else. And now we have our emitter with our collision terrain. And I think we've got our collision terrain. Let's take a look to see if we've got a collision field. No. So we've got a problem with our collision terrain now. I should have done everything next time. So I basically want to have collision source as my point to inside of here. So let's make sure that is correct. No, so I'm going to actually reference the collision source directly from in here. So the terrain, collision source. And there we go. I ended up doing it from scratch anyway. So now we have an emitter with the collider. And our container is way too big. Zoom out, spacebar B. We have a very large container, so I want to just go to the flip solver and just change the container size down. So that's going to be on the flip solver itself. You get the nice handles. Shift, click that down. And we've making the container so it fits around our collision object nicely. Let's pull that up. And once we have the container roughly where we want it, spacebar B again, we can now run our sim. Make sure that's okay. And now we want to peer into the various pieces of data that we have on our simulation. It's a fairly straightforward water sim, but now we want to take a look at what we can do to help break up the water. A lot of people call this air, adding air resistance or airflow into the fluid itself. And one of the things we want to do with the box itself is basically, we'll leave the container walls and cells for now. I don't know if we want the water to spill out or not, but collisions. We'll leave that in. So now the idea is there's all kinds of techniques about taking the particles themselves and messing around with the density. But what we want to do now is working on the volumes themselves. I open up the details view in the bottom. What we want to do now is work with the actual fields themselves to see if we can offer some interesting effects to the particles simulation to help break it up a lot sooner. What you'll find is the water will flow with not much character. And what we want to do is introduce some resistance to the particles themselves, so we can break up some of the effect of the, basically mimic air in a waterfall to try and help break the water up. And the first thing we can do is introduce curl into the fluid simulation. And if the flip solver has 3 inputs, the first left purple input is particles, then you have volume velocity, and then finally you have sourcing. So what I wanted to put down here is we're working with volumes in dots, and there's a great node in here called the what is it? I believe it's my brain's not complete. It's I know this off by heart. It is the maybe the Bob force, not Bob force, but it's a gas field Bob. I'm so sorry, gas field Bob. Oh, my brain just went. So the gas field Bob is an amazing node. it allows you to take any volume that's present on your simulation object and just have fun with it. And because the second purple input in the flip solver is where we get all the volumes from the particles, because the way the flip solver works is the particles are actually used to create volumes. And then it's these fields that are used to do all of the heavy lifting, and then the result is passed back onto the particles. So if we can work on the various fields prior to them going through the project non-divergence step, which adds all the nice swirliness, and then back into the pops, this is your tool. Now what we're going to do is we're going to dive inside of there, and we're going to open the flip object, and we can see in the details view for the flip object, there's some interesting volume data. The volume entries for the geometry that represents volumetric data or fields have a special icon on it that looks like a grid or a grid of point or a box full of points. And you can either have, for this case, a collision velocity. The collision entry in here actually represents a sim scalar field. So basically it's a field or a volume that's scalar, so it's a single float. And we also have collision vel, mass density, and we can see the initial value is 1,000. And we're going to investigate these various fields as we try and work up some interesting effects on a flip fluid. And then there's pressure, source, surface, velocity, and viscosity. We have viscosity set to 0, so it's, even though the field is there, it's being negated. So we're going to dive inside of the gas field VOP now. And as we saw with the other one, we use the bind VOPs to bring in the various fields so we can work on them. So we actually have the very first one, which is velocity. We're probably going to be messing with velocity, so we'll probably need to bring in the velocity. And we're just going to bring it in as a 3-floats vector. Although I do know the other one works as well, so we'll just bring it in as a 3-floats vector. Looks fine. And I'm going to blindly add all the other ones because we want to create a little bit of an environment where we're not encumbered by what we want to do. So we definitely want to bring in the collision volume, so which is an SDF, a sign distance function. And we might have to take for those of you, I don't know if everybody knows what an SDF is, sign distance function is, but we're going to definitely use one so that we only apply the curl to the outside boundary of our surface. And we'll see how we can use the collision volume for that. And finally, there's collision weights, collision vel. We're not going to be playing with the collision weights yet, but there were some questions about rigid body objects interacting with flip fluids. And that's where you get your measured collision weights, is in this particular field. So if you wanted to generate extra particles and stuff like that, you could use the collision weights field. And then mass density. So we definitely want to bring in the mass density as well. And with mass density, we can actually change the density of the fluid without actually changing any of the particles themselves. So we definitely want to play with mass density. And I have to be very wary of the type as well. So that's a scalar field, and that's a scalar field. Collision is a scalar field, but velocity is a vector field. If I press on the vel field, we can see that it's a sim vector field. So I brought it in as a 3-floats vector. There's also the pressure field. That can be interesting, and what that is it detects pressure within the fluid simulation, and then you can do prior to it being processed. So any buildup of pressure, we calculate that. But that's pretty much all that we want to do. And we might want to also get not the collision, but the surface field as well. And it's the surface field that is really interesting to me. And the surface field, again, is just a scalar field. So now, we have velocity. We also want to add a bind export. And everything is going to be driving into the velocity field, because everything is velocity. And I want this to be a 3-float vector. And I basically want to take my velocity in to velocity out. And now I should have absolutely no effect whatsoever. To help me design the system, I want to turn on a lot of the guide geometry that's available to me inside of the flip object. So under guides, I definitely want to have the velocity grid up. but it's in the wrong orientation for what I want to deal with right now. So I go in the velocity tab and I want to change it to the YZ plane. And now I can see the velocity from my flip fluid. You'll notice that the velocity, the way the setting is we cull it based on if the velocity is less than 0.001, we don't show the streamers. But you can be rest assured the velocity is 0 everywhere else. And that's the problem that we have with flip solvers, is that because the particles themselves hold the velocity after the time step, we lose all the rich velocity data around the particle simulation itself. And only the particles are storing that data. And that's why for when you're packing air or you want to simulate some air effects around the particles, you might want to turn to a different technique, which we're going to do in the second exercise when we use a smoke solver. So in the gas field VOP, we can now do some really horrible things. I can put down a constant, and in the constant, I can basically put a vector in here, and I can go 0, 1, 0. And I can add this to the velocity. I mean, always do this. First step, you're doing something new, see if it works. Do something really horrible. For instance, let's make this fluid float. So I'm going to add a velocity in y of 2, and you can already see the streamers already going up. So I know this is working, right? So that's the first step. Whatever you're doing, anything, make sure that it works. And of course, if I press forward from now on, the fluid is going to fly upwards. So we have implicit control over the entire simulation now. In this case, we're taking the particle velocity from the previous time step, mapped into the velocity field, represented by this guy. And then we're being brutal, writing a constant of 2. So I'm going to do File, Save As. I'm going to put the webinar. And press Accept. So now, so we can write into the velocity however we want. We don't want to do this though. So I'm going to wire that out. And let's go forward a couple frames. Let's see our nice velocity. We want to add some curl. So again, using the same thing, we're going to add curl noise. And curl noise. Once again, we're going to add the position in there for P. And then we can wire the curl noise into our add. So we're going to add curl noise to our flip fluid. Really straightforward stuff. Now we're adding curl everywhere. And we're basically, it's like the water is boiling, but it's working. And you can see what's happening here. So we definitely need to adjust the amplitude on the curl noise. But just knowing this alone, if you're not that aware with it or you're not that comfortable playing in this sort of a way, do what I did. Turn on the velocity guide, peer into the data, take a look at what's available to you, and start having some fun playing with this data. It is no different than what R&D does to develop a lot of these effects. When they see something very interesting, they will dive into these sorts of environments and start playing with the various data constructs. And if they need to have a piece of data that's not currently available, to go into the development environment and write a tool that will extract that data from the sim and give it to you in this environment. But that's the curl noise. We don't like the curl noise applied everywhere. We only want to apply it where it's necessary. So the first thing we want to do is we only want to apply the curl when the velocity of the particles are beyond a specific threshold. Let's say we only want to apply to the particles that are moving faster than, let's say, 2 meters per second. So what we can do is in the velocity, we can measure the amplitude of the velocity, and that's done with the length. So length is just basically Pythagoras, right? I think grade 7, at least in Ontario, you learn Pythagoras is grade 7. X plus y, squared plus y is better. So it basically allows you to calculate the length of or magnitude of a vector. So we know the speed. So basically the length is the speed in meters per second. Now we can threshold this and bound our curl noise. It's all about masks at this point in time. Compositing is all about masks. Filters and multiplying your values by filters. But we're going to be pretty hard in this particular case. We're actually going to say the speed, and we're going to actually put a compare node down. Compares are brutal in shaders unless you're really, really clear as to what you're doing, because they can lead to anti-aliasing. Everywhere else, start comparing. So we can compare the speed, and we can say if it's greater than or equal to 2, it will be true. So now what we can do is we can put down a two-way switch. So a two-way switch goes hand in hand with the compare, where we can put the Boolean operator in there and use input condition 1 if true. So if this is true, we're adding a curl noise. And you'll notice that we have these things called signatures inside of Vox. If you're unaware of that, if you have a float, a lot of these nodes will auto change their type based on what the input is. And the second input is going to be just our plain old velocity. So that's a really simple condition where we're taking the speed, comparing it. If it's greater than 2, use the curl noise. If it's not, don't use the curl noise. And then we're going to add that to the initial velocity. So step by step, we're adding a lot more interesting workflows now. And we probably want to make the curl noise frequency a lot higher. We can actually see where it's being applied. And let's go back to frame 1. So now the curl noise should only be applied when the particles go beyond that 2 meters per second. And sure enough, there you can see that it's breaking up when the particles are now starting to go beyond that speed limit threshold. But we can do even better than that. We have the surface field available to us. And the surface field is actually, it's an SDF, a sign distance function, representation of our water. And that sign distance function is used for many different things within the solver itself. We use that for seeing if some particles are ballistic or not, or how the white water flows on top of the flip solver. But if we go up to the flip object, we can actually take a look at that guide data for the surface, so we can actually see the surface field as well. And if we push forward a bit, you can see that's our surface field. And it's available to us, so why not use it? And the idea here is this special type of data, which is a sign distance function, we're actually telling the graphics card that where to render this surface, given that piece of that volumetric field called surface, because it's a continuous function. It's a continuous function field where wherever the value is 0, that's where we're currently saying the surface is, which we call the limit surface, or the limit value. And then everything inside, the further you go away from the surface, the more negative it becomes. And the further you go out of the surface, the more positive it becomes. And that's where we get this word signed. It's a signed distance from the surface. And the field represents a function. So that's why we call them sign distance functions, by the way. So we can actually go to the surface field. And knowing that, we have the ISO offset. So we can actually view where the limit surface is. So if you forget, all you have to remember is, oh yeah, ISO offset, I can offset any distance, and it's a continuous function. So that means I can go negative and see what happens. It shrinks it down. So it's exactly what I said. So every voxel within a sign distance function has a value, and that value is the distance to that 0 limit surface, or the closest surface, and that's what's available to me. So I can say, well, I'm only going to apply the curl when the ISO offset is between minus 0.05 maybe, and maybe 1.1, or if that's a bit too low, positive 1.1. So, oh, that's way too high. So 0.1. So it's, oh, pardon, 0.1. I meant 0.1. So we can actually say only apply the curl to the velocity field where the ISO surface is either going from minus 0.05, let's say, or that's even too harsh, minus 0.02 to 0.01. Sounds good. So we only want to apply curl to that piece of this, to that piece of the surface. Okay. So let's go back inside the gas field block, and we have our surface field. So we're going to add 2 more conditions, and we're going to put it down 2 compares, and I can see greater than, we put minus 0.02, I believe, right? Or we can change this so we want to compare inside collision. And we can actually pass the surface field into that. So now this is going to be true when when the voxel value is greater than minus 0.02. And I want to put down another compare. And what's it less than or equal to 0.0, I think we 0.1. And there we go. So we use the visualization data to figure out where those sweet spot values are on our surface field. Because remember, it's in scene units. That iso-offset distance, that distance that's computed inside of the SDF is signed, and it's the actual scene values. And now we're doing a simple compare here. So now we need to put down 2 two-ways. For those guys that are into hard coding, they're going, why am I not writing this in a Wrangler or using a snippet? Yeah, you can do that, but let's keep things graphical. It's the same thing. So the input one is going to be, so now we need to start worrying about how this is all going to work with our curl noise. So ultimately, we just want to create a mask. And the mask means multiply, right? So we're going to need a multiply often here, because we want to multiply the results of whatever this is into what it is we want. And so we have our two-way that's now working on the velocity threshold. So that's step one. Step two is we now want to take the result of this. Actually, we only want to apply the curl noise after we do the compare. So let's move this over to here. And so now we want to take this noise here, and this will always be the second input. Okay, so we're going to compare, and we're going to say if that's no, I'm sorry, what am I doing? So basically we have a two-way here, and this is the two-way that I want to work on. So if it's greater than 0.01, I want to apply the curl noise. So let's wire the curl noise into here. Okay. And if not, we want to wire that basically into our velocity. Same thing with the second two-way. So the result of the first two-way, which means am I above the surface, that's great. Now we got to say, well, if I'm too far out, again, oh, what am I doing? I didn't want to do that with the compare. Sorry. I just undid that. I want to do another two-way. And again, the condition is going to be from the second compare. And I want to take the result of the first one. And again, if nothing's happening, I just want to take the base velocity and just pass that through. Now I can wire this into the velocity threshold. So now I have my conditions. So basically, I'm only applying the curl noise between when it's greater than minus 0.02 or less than 0.01 on my surface. So my surface bounds. So that's that boundary that I want to apply the curl noise to. And secondly, when the velocity threshold is greater than or greater than the speed that I've defined. And now let's play forward and see what we got. And it's just zipping along now. So that's the advop bind. Now I got to make sure that I'm doing everything correctly here. So the speed is greater than 2. I'm getting runaway, and the chances are it's because the curl noise is, let's make sure my boundaries are correct. That's 0.01. That's equal to 0.01. And so curl noise, and then I'm taking the results of that, and then I'm applying it to the two-way. So just my speed. Let's make sure here. It's 2A, 2A. Well, let me take a look at the file that I wired up earlier. As I said before, I might need to have a look at that. Gas field VOP. And there's my curl noise. Multiply. I'm just wondering what I did. Oh, I'm just wondering what I did to make sure that it didn't screw up. So there's my surface. Compare. I used an AND. That's what I'm screwing up. I'm so sorry. So yeah. So instead of doing this, I can actually do it. Yeah. And that's what I wanted to add. So basically, we have several type of conditions. We have OR as well. So we can choose when one or the other is true absolutely, or when one or the other is true. And that's the AND that I wanted to wire in. And that's what I wanted to put into two-way. And this means we don't need that one two-way. So basically, I was saying everything is true. It's still flying right off, so.
It's not like we were saying 2A2, 2A2 must have 0.
Let me check that. So that's actually, yes, I have to make sure that this input one if condition is true. Yeah, this was working so nicely. Volume gradient file, so this is compare, and so that's not what I want. And so that's basically when that's there, and then that's there, do the two-way. I know this one works, so I might go with this one for now. Well, pardon me, yeah, there's my two-way condition. And I probably want to, oh, you know what I'm doing wrong? Yeah, I know what I'm doing wrong. So I have one condition here, and I need to do another AND. So I want to put another condition in here. So I'm going to say when that is true, and when that is true, then wire that into the two-way. So the two-way will then apply curl noise. Only when all those conditions are true. And if not, just pass through the regular velocity. And sometimes I need to make absolutely sure that the simulation is recalced. And I still have runaway velocities, so I've probably got too much curl noise. So let's set that amplitude a lot lower. Still taking off. So the speed, compare greater than 2. And compare inside, outside, my surface field. Yeah, I'm going to go to the other file again. So what I did in the file that I know works is, and we'll take a look at that now, because I want to move on and keep on going. Okay, so I'm going to move now to the file that I know worked up. I actually worked up the same way organically, so sometimes you get a home run, sometimes you don't. So this is what I did right off the bat, just what I was jamming with you guys before, and yeah, yeah. So and I created the same way organically a couple days ago, so this should be fine. So the gas field.
Andreas said there was an error in the addition because they're all that.
Oh, that's probably right. And I'm probably Russian, which is never a good thing. So velocity, calculate the length, as I said before, compare it greater than 2. And then I do another compare down here with the surface field. So we know that's it's basically an offset value, and that as well. So that's so far so good. Do another condition, and then that goes into a two-way. And then I take the velocity, and I add that to the combination of the curl noise, which is using, I've also added some time into the offset of the curl. And then simply multiplying that. Oh, that's what I did. I actually clamped the velocity, okay? So I think I ran into the same problem before where you can get runaway velocities. So I ended up just basically, yes, I did this instinctively, and today it's not coming to me, so I'm very upset about that. So the length, we're actually comparing it to a length of 2, right? So that means we've got a velocity of 2, if we're true, rushing into this whole thing. And so what I did is that you have to subtract the magnitude that we're adding. Okay, so because coming into here, we already have a threshold velocity of 2, and it's just going to scream, which is what we're seeing. So instinctively, I even added the subtract the velocity of 2 even before I ran it. And then you clamp it just to make sure that you don't have runaway velocities, and then you multiply add and then the 2 ways. So basically, it's what I had before. So let's see if we can rescue that one last time, and then we'll go to the other one to see what I'm doing with the density field. So again, I want to do a subtract constant. Hello. So I want to take the subtracted constant, basically subtract from the length of the velocity of 2. And then what I want to do is just do a multiply and cut that way back. So I want to scale, and let's add a promote a parameter in here, and let's set that, put it scale, and set the default value to 0. Let's try 1 for now. And then this is what we also want to multiply the value going out as well. So let's and then you probably want to put the velocity in first. Right here. And then I'll rearrange my multiplies. And then finally, that is what I want to put out. Let's see if that works. Much better. And then it screams away because we have so much velocity. So we're now applying the velocity exactly where we want it. And I forgot my clamp. So let me put a clamp in there. And then clamp it to 0.1 or 0.2 or let's clamp it very heavily at first to make sure that we're not injecting too much curl. And now we're starting to get the breakup that I wanted to get. So now we're only putting curl exactly where we want it. So I'll save this file out and take a look at the other example file that I had working on. And I added one more thing as we were going forward, is the density field. So if I go up to the flip fluid object, I'm going to turn on my density field now. And as I play forward, we can see the density grid. And we default density to 1,000. If we take a look at the density grid, I bet you a lot of you never even looked at the density visualizer grid in Flip Solver. That's one of the things you want to do when you want to work with fluids. Generally, when it aerates, it gets lighter, or it seems it gets lighter as it's not as dense. It's just one way of faking it. So by playing around with the density in that same narrow band field, by once again using the collision as an ISO offset, you can actually pinpoint exactly where you want to reduce the density. But it defaults to 1,000, right? So back again in the gas field dot, I have a different set of logic for the density. So I took the mass density, again, doing exactly what I did before, running a two-way again on the compare if the velocity is greater than 2. And in this case, I found out that the air, I wanted to etch it a little bit further into the surface. So I wanted to have different controls as to where I wanted to apply the density. So basically just skimming of the surface. And then so basically anything that's outside of the surface by 0.05 units and just etching into the surface ever so slightly, minus 0.001, I can now modify the density of that volume. So if I press forward now, Now you can see I'm also affecting the density, exactly where I want it to do as well. So we've taken that really boring simulation, which was just fluid falling over a waterfall, and by using just working with the fields themselves and not even bothering with the particles themselves, we can do some really cool things. And so this was just hacking away and working on things. Having said that, if you've ever peered inside of the flip solver and the pyro solver, every once in a while you're going to run into one of these gas field box where we're doing some very interesting things with the various fields available to us. So again, we now have some really nice early breakup, and this is just a rough sketch. I mean, I really haven't even begun really fine-tuning that and seeing what parameters I can raise up to the artist and that. But what's really nice and lightweight about this one is it's seemingly good for waterfalls, where you're not really packing air, such as a spacecraft just coming out of the water and the water pouring off the spacecraft. This is more for fluids that are continually flowing, and you just want to break them up to add some interesting character. And that's exactly what we're doing right now. So now you can see that we're injecting the curl only where the velocity is greater and only on the surface of the fluid. So that means that if there's some velocity up here, we might get some bulk fluid. You can see we got some collisions against the walls. Some work for you guys. For the more advanced users out there, and I've done this myself, another file is the surface field. You guys all know, some of you know that you can calculate the gradient from the surface field. And the gradient is basically the surface normal if you extrapolate the zero field. So if you know where the surface is, and you know the surface normal, you can then do a simple dot product. And that dot product will tell you whether or not the fluid is moving downwards or upwards. And there you can use that as yet another condition as to where you want to apply curl noise, the density, and all the other effects you might want to do. So all of that is available to you once you know you got this surface field done. So that's the first field, the first file. So I'm going to just go ahead and quit this. I'm going to save this guy. Now I want to show you another file. And I have another file which is based on some cool ideas from way back on Battleship, ILM, and they used this really cool technique where they calculated the velocity field from rigid body collisions, and then they used that velocity field to help guide the flip fluid simulation. We do like, we do like, yeah, that's funny. We do like the compactness that really gives us, and sometimes we don't want to run multiple sims. So what I did is I actually created a scene file, again, where I'll show you the final file, which is float. Is that the one I want? No, I want drop air. So there's two types of things we want to do. So basically, this scene file, and I'll show you the scene file that I'm working on here. This guy here. So this is just a really simple test. There's a tremendous amount of wind in here. Some of you were asking about wind. How do you inject wind inside of your flip fluids, inside of fields? So I do that as well. So in this particular scene, there's a lot of wind in here that I'm pushing the fluid. But you'll notice that the fluid is actually, in this case, using a gas. It's actually using a fluid solver in a smoke solver to add buoyancy and resistance to the flip simulation. And I use the collision field from the flip fluid as a collider for the velocity field. And then the velocity field gets used by the flip solver pretty much automatically, and we'll show you how to do that. So, and I have another flip here that's a little bit different, lower resolution. But, you know, imagine a big ship rising up from the water and you want to basically have it pack air, and the ship has all the air, and you want to be able to add your own turbulence, your own curl, and everything else related to that. So I'm going to take a side view here And hopefully this is the lower resolution one, and I'll play forward a bit. Actually, I will lower the particle separation a bit, so you guys can get an idea of that. So let's set it to 7.07. See if that gives us a reasonable speed. Okay, so what I'm doing in this particular scene file is I have a lot of control as to what it is that I'm doing. You'll notice that I'll give it the pyro solver. There's a smoke solver in here, and the flip fluid object actually has that collision field present to it. And the collision field, or pardon me, not the collision, the surface field. There is a way for just a generic smoke solver, and what I did with this is I just added a smoke container and resized it, and basically I channel referenced it manually to my flip fluid object, or from my flip solver has the under volume limits, box size and box center is where it defines the container size. And I just channel reference it to a plain old smoke object I just created, and then I put it in the smoke solver. Then I did some really interesting things in here. So first of all, right off the bat, I'm going to unwire my gas calculate, and I'm going to unwire my merge. And the merge is actually going into the velocity update. So I'm doing an awful lot of work on the velocity field in the smoke solver. And this merge dot couples the flip solver with the smoke solver. And that means that the velocity from the smoke solver is actually going to be picked up by the flip solver. And all I needed to do in the smoke solver to pick up that collision surface is in the relationships collision tab, enable use volume velocity for collisions. But the more important one is collide with non-SDF. So there's a mechanism, or there's a mechanism built inside of the smoke solver such that if it's colliding against any simulation object in the scene, it will try and compute an SDF from those fields that are non-SDF. And the surface field is considered to be sort of a non-SDF. So by enabling this, all of a sudden my smoke solver now has, if I go to the smoke object here, and I go to visualization, I turn on velocity here, all of a sudden starts to show velocity effect. So now I actually have my velocity field reacting to my flip fluid. And the velocity field is being used by the flip fluid. And just to show you the radical difference between being able to calculate a velocity field from my flip object, if I go turn the smoke object velocity off, I go to the flip object and turn its velocity on, there you go. That's your problem with flip. Is it tends to give you very uniform velocities that are very challenging to work with. So if we can use this velocity field from the smoke solver on our flip solver, then we're doing some really cool things. We're able to do some really cool things with our fluid. So inside of the merge, I'm going to wire the merge into the second smoke solver, and I'm going to bypass my gas turbulence, bypass the gas local sharpen, and bypass the gas wind. So the only node I'm using right now is I added a gas vortex confinement to the smoke solver. And what gas vortex confinement does is it takes a look at, it's basically gas vortex confinement is a way of describing, you know, when an airplane wing goes through the air, those cool vortices from the laminar flow that it calculates. Gas vortex confinement gives you all of that data and constructs that data into the velocity field. And we can turn on the visualization of that. And then if I press forward, and the confinement scale is pretty high because we're dealing with a density of 1,000 in our water. So the confinement scale has to be pretty high in order to see it. And so now you can see we're actually, the gas vortex confinement is detecting. So it'll give us those nice eddies and swirls when the fluid starts to fall down. And if we really scale this up a lot, we're going to get a lot of, you can already see that the water is folding back now because it's interacting with that velocity field. So you remember the mushroom crowds you always get with pyro, and you don't want that? Well, with water falling, you kind of do want the water to slow down as it interacts with another velocity field. And you can see the gas vortex confinement is doing some really cool stuff to the flip fluid. So we are getting some nice, interesting effects on our flip fluid. And of course, what we did in the other scene, if you want to go in here and figure out work with the density, you can absolutely do that in here as well. I mean, this one I just focused on that. So you can actually make the fluid lighter when it starts to move, when it gets impacted in different ways by the smoke solver over here. So the only problem you have, though, is gas turbulence. If you just want to add generic turbulence using the gas turbulence dock, it really wants to have a density field. And because I just created a plain Jane smoke solver that has no sources, it has no sources on it, believe it or not. It's just a smoke container with a velocity grid that's being impacted by other collision objects. I kind of need to create a density field. And that's where gas calculate comes in. Gas calculate is a great way where I can take one of the fields that's present in the smoke object. It's already built itself a collision field that I'm importing from the flip fluid. So I'm just cheekily taking that collision field and creating a cheap density field so that the gas turbulence and the gas local sharp and the gas wind will work. Because gas wind really likes to have a density field as well as a mask. So cheekily I'm creating a density, I'm populating the density field, which is there by default. I'm using the collision field as a source. And in the destination fields over here, pre-multiply it by 10 because I just want to scale it up because in SDF, remember, it's going to go from 0.01 because it's a continuous function as you move away from the surface, so I wanted to scale it up. And I want to take the absolute value, so if it's negative inside, I want to make it positive. So that absolutes that. And then finally, that's it, just copy it over. So now you can see I've got a little puff of smoke as well. And all of that is being, I didn't want to do that. Before was that? I think I did it on the crumble change. There we go. So I'm just basically calculating the density from the volume. And now the gas turbulence will work. So if I go to the gas, enable the gas turbulence, and now I can put the turbulence exactly where I want it to go. I'm just going to turn off the visualize on my vortex confinement and turn on the visualize on my gas turbulence. Now, with the gas turbulence, I need the turbulence settings, pretty high scale of 4. Swirl size is a bit small. But if I press forward, you'll start to see that I can apply the turbulence wherever I want. You can see there's some on the ground as well. And let me zoom in on that. So now I'm applying turbulence to the fluid as well. And as I said before, everything you do in this velocity field will be used as an effector on my flip fluid as well, because the sims are coupled. And the gas turbulence, if I go to the control settings, I'm not even using control settings. I'm basically I'm just calculating the gas turbulence based on the density. So I'm not even using a threshold on the density as well, which I could do. And now that helps break up the fluid a lot more. And now that I can control my flip fluid with a smoke solver coupled together, any gas field type node will work. Let's add some gas wind. You can add fluid effects on top of the velocity field as well. So gas wind is now adding the wind direction of 1 unit to the left. And if I press forward now, we're actually adding wind to the, and let me turn the collision field off on the flip fluid because I think we get the idea now. So the smoke solver, I'll just make sure the collision is off on the flip fluid. Turn the surface field off. And there you go. So stepping back a bit, there's a really cool paper from Bridson a few years back where he talks about over-simulating a container and filling it up with particles. And if you fill that container up completely with particles, with much lighter density air particles, you get this really cool effect. The only problem is it's a huge overhead because the particle density is there. So if we can come up with a different way of providing a similar sort of a data construct that's a lot lighter, and the resolution of my smoke sim is quite low actually. I think it's I think my division size. I got a coupled, and I think I cut it in half again. So it's running at a much lower resolution, or you can run it at whatever resolution if you want. I also do not have a resizing domain on here. I could add a resizing domain to get it a lot more efficient in terms of providing air impact on the water. But so instead of using the particles to hold on to all the velocity data, in other words, filling the whole container up with a low-resolution particle grid to hold on to the velocity, I'm utilizing Houdini's dops. I'm just saying, nah, screw that. I'm going to use a smoke solver with a smoke object to hold on to that velocity field between the time steps. So stepping back a bit further for the more advanced users, you're now going, okay, so now I can use a grid to store some of the data around a flip solver? And the answer is, yeah, if it's velocity, you can use the smoke solver right off the bat. But if you want to create another object, or actually add some extra volumetric data on top of your flip object, you can do that as well. But look at the nice breakup I'm getting there. And I'm being really crude here. I haven't even begun to refine this at all. Just the very fact that we can add gas-like properties to a flip fluid within a single sim, it's a lot of fun. So again, proof of concept is working pretty good. And you'll notice that as the simulation starts to run, it starts to get a lot more interesting. I'm a big fan of trying to simplify things into one area and not having to do so many cascading simulations to these effects. So hopefully you guys will get this file and you can have some more fun with it. It's just yet another way. You know, there's a few very popular threads on OddForce that deal with air and flip fluids. So I'm just sort of throwing these two ideas into the mix as well. So that's that. So, and again, this time there's no VOPs. If you want to use a gas field VOP in here, go right ahead. And as I said before, the flip solver actually did something in here. Pop it vec by volumes. I did need this probably. I'm sorry, I did miss this step right here, which is mandatory. On the flip solver, there's a volume velocity input. In order to pick up the velocity from the smoke solver and apply it to a flip solver, you need to use the simple pop-it vec by volumes. And the pop-it vec by volumes has a velocity source, and I'm going to say the dot data. And I basically just click the smoke object. So this is what's grabbing the velocity field. So if I wanted to bring in a collision field, I can do that as well. If I wanted to bring in a density field, the flip solver doesn't use density, but I can do that as well. So any fields that you want to bring and modify, or modify directly from the smoke solver, you need this stuff. So I should actually rename this just to make sure. Smoke solver. There you go. So that's that. Lots of fun files there. I'm going to comment it heavily after the session and then make the files available to you guys later today if you want to peer into them. And now for a little bit of a look at whitewater. So I'm going to quit this. So I'm doing a couple things for you guys out there. I asked for the various files that we're using to show Houdini 15 and 15.5 fluids. There's the old bubbles in water. I think that's in a help card example. But the distributed river is a great file to have. So I'm in the process of cleaning this one up and commenting it very greatly. These files were developed while the flip tools were being created. So the nice thing about cleaning up these files is that it's actually simplifying them greatly, because when we were prototyping this stuff, there was a lot more errant nodes in there. So, and these are the files that we use to generate all of these various movies for. Hopefully these are playing back for you okay. This movie is showing you the distribution of the whitewater itself. And in this case, the white water is just basically rendered as spheres, as semi-transparent spheres, which is fairly effective for rendering some stuff. And then there's the distributed low res. So this is basically just the low res again with the fluid. So these are really good example files. And as well, it shows how the files have in them the ability to distribute across multiple machines, which is how you get the high resolution. And as well, volume frustum of just the fluid, so of just the white water. So the white water is only working on where the camera frustum is located. So I'll clean that files up for you. And next is the Osprey Rising, which is a great file. And this one, this file is pretty interesting. We're gonna pop it open and take a look at some of the techniques that were done to render the particles, because they were rendering the particles as point cloud, as a deferred geometry lookup, but basically rendering them as with a constant shader, believe it or not, with just some transparency. And for the most part, the white water on here is at its defaults. I think Scott did a really good job of describing how to tune the white water. I think about almost a year ago, and that still holds true with a lot of the various fields. The next release will see a great improvement in the white water, which is something we can't look at right now. And then the river scene, which is what we're going to look at next. So there's a basic scene in here, and it generates some nice velocity with some nice white water. And in this case, we're rendering the white water both as particles and as steam. And so these files I'll clean up for you. I do want to take a look at the river scene. Let's take a look at this guy. And then we'll just field a whole bunch of questions and we'll see what's up. So this particular scene, really straightforward. We just have a simple river with some obstacles, simple fluid simulation, which I've cached a bunch of files to disk already. So I'm actually going to go into the river fluid and import. I'm going to load from disk. I think I've got a few frames loaded up. So I can probably go. I think I've got, how many frames do I have cached out so far? 77, which is good enough. So let me go to frame 75. That should be cached at this. So import the river. I'm going to hide everything else because I think I'm clicking everything else. So import the river, frame 74, 75. So this is giving us an interesting field to work with. How many particles do we have? We have about 3 million particles in the simulation right now. And this was done prior to the compact fluid, so I'll definitely modernize this one to the. I actually have another file that actually uses the new compressed fluid workflow, which is a lot faster. But the white water is roughly the same. And in the white water generation, so if I go to the white water source, as we all know, this is key to getting your white water going correctly. So the white water source generates three types of data that we need to simulate with. So it interrogates the particles coming in, and it uses all the information we have available to us, the surface field, the velocity field, and the points themselves. And so we can choose how we want to emit that, basically the emission from the depth. And this is actually using, as we saw before, the sine distance function of the surface field. So we now know that we can etch inside of it, and we can go a little bit further outwards if we want to, or we can go a bit deeper, and we can change the emission rate, curvature, acceleration. But how to render these is, so I'm going to actually go, and unfortunately I didn't have the time to sim out the actual whitewater. So let's see, because the whitewater is at the defaults, right? So if I press forward, I want to see how quickly this sims up so we can get some whitewater to start to render. So we have some whitewater being generated, and as we know, there's 3 different types of whitewater. If we middle mouse on it, we should have the 3 groups. There's a lot of groups. We have bubbles, spray, and we should also have foam. So there's a lot of foam. So let's use a blast node, and this is all net new, right? This is what is not covered on the shelf. So let's actually just work on the foam right now. See where our foam bubbles are. Take a look at that. That should actually simulate up a bit further. Now the foam is good. Go ahead. Yeah, there we go. I just saw that now. So, so in the foam, and you have to do this for the foam. Generally, there's a few different ways that you can approach this, depending on how close or how far away you are from the surface. But generally, foam is something that you might render in a couple different ways, depending on what is it you want to do. You can actually copy geometry to it. Depends on how many particles you have. This is fairly low resolution, so you can certainly use instant spheres, semi-transparent instant spheres to do this. You can also use blobbies as well. So I'm going to show you a bit of the blobby technique using metaballs because it's fairly fast and there's a really good match procedural for that. So out, foam. And what I want to do is create a new object called foam. And I want to render the foam. And bring that in. So we're going to do this inside object merge. And the object I want to bring in is out foam. And into this object. So now I have my foam. And I can go up. Now I can apply a specific shader to the material palette. By default, we just add just a basic noise So we're going to actually render this as we're going to render it as smoke for now. So we're going to put down a basic smoke. Actually, we're going to put down two materials: a basic smoke, as well as we're going to basically using a mantra surface. Yeah, these blue smoke. So we're going to try both of these shaders on our foam. And let's go back to OBJ. Zoom in here a bit. I'm going to focus on this bit of foam over here. Hopefully that's on the surface. Yes, it is. Kind of. And I'm just going to add a quick camera there. And for now, I'm just going to turn off the water just to make sure that I can actually see it. So turn off my white water source. White water. Oh. And under material, we can choose. First of all, let's take a look at the mantra surface, and we probably want to change some of the parameters. Just hold Control click on the jump arrow, opens up the parameters for that. Just Control click right. And I basically want to go under. I'm just going to make this really straightforward. I'm just going to add some transparency to it for now. I go to opacity, and I'm going to set the opacity scale at 5. And I might also add some. Actually, let's leave opacity to 1, and let's do. Let's go to opacity 0.5. So it really low. And so you can approach it from the foam rendering that way. And let's see under R. 2. And let me go back again. So, yeah, let me find out where that geometry is coming from. Okay, all these off. There we go. Yeah, somebody we copied spheres. So there's my phone. I'm just going to go to the render view and hit render again. So that's just rendered as spheres with their standard foam shader. And so if I dive inside of this, we can do a few other things to improve this. We can take a metaball. And as I said, we can use a copy operator. And metaball, because it's going to be using a p-scale attribute on here if it's present. Is p-scale? Yes, it is. So the metaball's got a radius of 1. We're going to set it to 0.5. And then we can copy metaballs to the copy. I'll never display them, by the way, and I'll never select them. I might want to use and the copy operator, make sure that I have basically, yeah, that's all good. So, and I'm just going to put that on, move my display render flag onto the copy. And there's some options in Mantra itself that now will render them as metaballs, as blobbies, which helps out a lot. And so, under render, yeah, so if I go under geometry, render points as spheres, we could also render them as circles, but metaballs as volume is what I wanted to go for as well. So we can render the foam as just point. I'm going to put foam here as particles. That's probably foam surface. And I'm going to copy and paste this and call this foam metaballs volume. And turn the display off with this. Let's actually just do, you can see it just regular surface. So you can add transparency, some basic surface scattering. It works fairly well for far away foam. But for some foam that's a bit closer, you might want to use the same metaballs, but this time use the option here called metaballs as volume. I showed that the last time. It's really useful. But now we need to apply a volumetric shader to our surface so we can then do the billowy smoke. And it's a fairly cheap way of rendering volumes as well. There was a question from somebody before that we got in the last couple of days. Let's make sure that it's rendered. I might actually have to make that higher density. 10, 100. Yeah. So geometry, there you go. Render metaballs as volume, hit render again. I didn't have the option checked. And there we go. Now, when you're using render metaballs as volumes, there's some things that it'll use density. So if you have density attributes on your points, it'll use that. It'll use p-scale. So the only problem is the sampling of these volumes specifically uses a similar sort of sampling that we use for constant tile volumes, where the volume quality and the shading quality determines how smoothly or how coarsely they get rendered. So under under sample, pardon me, under I mean, we can go to the output driver now and hard force it. So let's press on that. And basically, it's a balance between where's the volume step size. I want the volume shading quality. Volume shading quality. That's going to be under polygon render. That's what I want. Something. What is this? Oh, this is an old Mantra rod. Sorry. Mantra 2. That's better. This is using the wrong Mantra rod. So this one, you actually have volume quality. So you have to increase the volume quality. And stochastic transparency is probably biting me right now. So you can get them fairly smooth that way. And then you can go to the density shader itself. And in the material palette under this billowy smoke shader, you can increase the density a lot. 1,000 if you want. Take the 10. And this gives you the nice scattering as well and the nice accumulation of the light as well. And so that works okay for the phone. So as far as rendering, foam's the trickiest one to get along, to get on top of. And of course, nothing's stopping you from rendering both. So if you etch the surface down a bit and you have some smoke on top of it, it also will look pretty nice as well. So you can combine both surfaces and volumes. And I think I turned the volume on the first one, so it's turned on. So you have a surface behind the volume. It's okay. And as far as I'd say for the spray, again, in that case, I just rendered points, tons and tons of very small points. And the bubbles, points copied spheres. If you really want to see just copy spheres to the points and apply the same shader as the water, the liquid shader. Just combine them with the liquid surface shader, merge them in, and it'll find that. So I'll open to questions now.
Okay, so this may sound kind of random. Let's see from the start.
Okay.
So when it's time, I think it's OpenGL helps speed up things.
I think there's a lot in the area of GPUs in the next release, which is in beta right now. So we are taking more and more advantage of the GPU as we go forward for sure.
Next question. So I'm just curious if you're specifically working with 12 scale. How does that affect the result of the same?
Not as much as you'd like it to, although we do say it does. The behavior of the sim scale does have a play in the types of units that we use with regards to floating point support. But I usually like keeping things at meters just because all the values that you're used to make sense. For doing, for instance, if you wanted to do a laminar type of a flow, which I actually have a file in here, which I'll take a look at. For macro scaled water, you could do a macro scaled water that had water flowing 10 meters, and you can still make it look beautifully laminar or fairly laminar and make it look more macro in scope. So as far as determining what's open water, waterfalls, or close liquid sims where there's surface tension involved in that, scale gives you the values that are good to start off with, but ultimately, do you want to start playing with different scales? Go for it. The forces you apply have to be adjusted. But obviously, if you go way too big or way too small, you're going to run into precision errors. And to be safe, all of the parameters and all of the defaults are set up to work with meters. So if you start decreasing the scale to centimeters or increasing the scale or moving into imperial versus metric, you're going to be futzing with those parameters until you basically cut it to where you were with meters. So, and we don't do that. So we just adjust the forces that are involved with the sims. None of the presets on the shelf tool get adjusted. For instance, power or flip. So best to keep it at meters if you want to use our values. But I said I was going to take a look at the laminar flow, and so let me take a look at this one, laminar flow. So in this particular file, it's falling, it's the same file as before. I mean, the liquid is still following. This is why I created this. The liquid's still following 4 units, or the equivalent of 4 meters. And instead of encouraging the breakup of the water, this particular file tries to keep the water looking more laminar, or more macro scale, even though it's falling 4 meters. And in this particular example, the point here is all about the velocity transfer of the particles into the grids that are used by the flip solver. And if you take a look here, you can take a look at this particular scene. So that's a great question with regards to scale, and I have this file ready to go. In this flip solver, we can take a look at the way the velocities are handled. We have a new swirly kernel in 15.5, and I'm going to use the viewport snapshots. If you don't know where these are, there's the memory toolbar, and you can go to view, and you can take a snapshot of any view you want. So if we go to snapshot, frame 30, we can take a snapshot at 1. Press the I and take a snapshot at 1. And then we can go and change all of this. We can take a look at the splashy kernel. And the splashy kernel goes all the way back to, and the velocity smoothing in the force scale has a big deal, and many of us don't play with these enough. Force scale imparts the amount of velocity. Amount of velocity is calculated by the sim gets applied to the particle, so it's a force scale. So we can actually have a lot more of the particle velocity carrying in, carry forward. And velocity smoothing means how much of the neighboring velocities do we want to use to reinforce the particle. So if I do force scale of, let's say, 0.5 and velocity smoothing of 1, and I run up to that same frame 30, shouldn't take that long, you'll notice that the boundary changes a lot. And people complain about, how flip generates the holes too quickly or not quickly enough. And you can impart some effect on that by playing around with velocity scale and, or probably force scale and velocity smoothing. So you can see here it has a completely different look at it if I go to frame 30, that is. And then we can compare this with the snapshot. You'll see that it's radically different. And you notice that the water's tightened up a bit. So definitely, when you have some idle time, generate a simple scene like this and start playing around with force scale and velocity smoothing. Setting force scale to 0 and velocity smoothing to 0, which means we're now using all the velocity as calculated directly from the projectile divergence. So hopefully this will give me a very chaotic, let me shoot my force scale 0. Force scale of 1 and velocity smoothing is 0. So we're taking all the velocity, and then we're not taking any of the neighboring velocity, and we're just basically pumping out the raw velocities outwards. So hopefully we'll get more chaotic motion if that fluid's going to fall. Oh, there it comes. And you'll notice that now the fluid is a lot more chaotic. Let's go to frame 30 again. And I changed my camera view, stupid Jeff. And so there you go. So you can see that it's quite a lot different again. So these two values for the splashy kernel make a big difference. And then how you update the surface as well determines how accurate the velocities are as well. Again, if you're doing macro sims, you can run less particles to get you nice flows. I set them to rebuild. The default is add vec. So basically the surface field, to make things faster, we just take the surface field from the previous frame and literally just pull it along with the velocity, vectored by the velocity. But if you want to have a much more accurate surface field, you can rebuild it every frame from the particles. So you can do that. Same thing with the velocity. Velocity is generally advected through the simulation from the particles into the field. Or you can rebuild the velocity field of your frame if you want as well to get more accurate sims. So next question.
What is the best approach to get an animated geo into flip? So the flip simulation follows the animation?
Yes, that one is, we covered that in the last one, and that one shouldn't be that should be very easy to do as well. Basically, just put down a sphere, and we're just going to put some noise on it. I mean, this one's literally a minute to play around with. Put down a mountain, and the mountain's going to be animated. And the answer is use the shelf, and I'll show you how to do that. So the frequency, the height is that, and the offset, let's put $T in here. Hopefully that's good enough. So it's deforming geometry, and we're going to animate it across our scene. So I'm going to use the decay key here, and then let me go to frame 24, and we're going to pull it through our fluid. Decay key, so it's going from there to there, frame 24. And now we're just going to add, under Ocean Effects, we're just going to add a flat tank. And there's a flat tank. And now all I need to do is go back up to the object scene, select my sphere object, and then go under rigid bodies. And that's what the deforming object is all about. If I press on that, it'll take any cache from disk. Essentially, putting a mountain top under geometry is the equivalent to importing a scene from disk, either in the limbic cache or whatever, and then you get your interactions. And the deforming geometry is now interacting with my fluid. Again, watch the previous webinar on how to make sure that your colliders are working correctly and everything else is properly defined. But now you can see that the fluid is deforming against a deforming object. Hopefully that will answer that question.
Okay, so next we have a set of three questions. Let me read them all first. And
okay.
Then we can go through them. One, is there a way to make a flip tank act as a container? You have collision for geometry as well as for particles. Question two, could you give one example of using white water shelf tube to create bubbles only from the object dropped into the water? And three, could you just give one example of using a right drop with a flip fluid sim? All the examples that you see are pyrosims.
Okay, yeah, so we can do all three. So is there a way to make a flip tank act as a container to have collision for geometry? So that means the flip tank container actually is as a collider. I'm not directly, but I can show you a way to do that so that it gives you the same thing. It should be fairly straightforward to do. So collision for, is that for geometry? Yeah. Okay.
Oh, yeah, for geometry.
As well as just particles. We can have a look at that, how I would set that up. So except that shouldn't take very long at all. So file new. So let's just put down a regular container. Again, go to Ocean Effects, put down a flat tank. And I think the idea here is, the question is, the container should also be a collider. I believe that's what the question is all about. So if I go, go up, and go into the flat tank flip sim. So I know it's going to be in the flip solver. Volume limits. And we can see that it's all tied into, I'm just going to break the connection on the size, delete channels. I'm just going to, well, actually, you know what, we should actually jump to that object, which is flat tank initial. So let's go to flat tank initial and change the, I'm just making the tank a bit smaller. Okay, making it a bit taller. And then we'll just put down I'll just put down a sphere again. And we'll have the sphere drop down onto the fluid. And I think the question is, the sphere just wants to fall down, and you also want to have, no matter where the container is, to have the sphere bounce around and fly on the container. So we're going to just take the sphere and fly it in the Z direction. So let's just add a rigid body and just put down a rigid body object. Go into a flat tank sim. And we're going to just give the sphere a lot of healthy velocity in the Z direction, say 5 units, and it should fly right off. And the question is, can I have this container as a collision object? Probably the best way to do that is to just simply build another rigid body object that's being driven by the container itself. And I'm going to see if I can do this from scratch. So I'm going to put down a static object along with a static solver and wire these together. And the static solver I'm going to put into the merge as well and make sure it comes first. The shelf tool does all of this for you, right? But the reason why it has to come first is because it's the easiest to resolve, and it's generate a one-way coupling, a one-way dependency to the other solver, so it makes sense that it comes first. And the static solver, there's actually some internal geometry inside of the static object, I believe. Is there? Yeah, SDF geometry. Does the static object actually come with its own geometry? A lot of these do. I'm just taking a look to see if they do. No, self-path. No, it does not. So possibly the best way to do this is to, two ways I'm thinking is just to build a box that references the flip solver's parameters. So I'm going to pop this open, say parameters. I'm going to go up. I'm going to add a box. And inside of the box, I'm just literally going to copy and paste those parameters. Copy parameter. And paste copied relative reference, or paste copied reference, I mean, in the center. Copy parameter. Then paste copied reference. And the problem we have with a box as an exterior collider, it's going to work great, but not as an interior collider, because our primitive normals are facing the wrong direction for what we really want to do. So I hit the escape key. You can see the primitive normals are actually facing outwards. If we want to turn this into an inside collider, we could try a reverse op. And if that doesn't work, then we have to add some thickness to our box. But first of all, let's try reversing this and seeing if this goes. And let's call this box collider. But no, the question is there's no way to directly turn that container into a collider. So the static object, the saw path, is going to be our box collider.
I just want to rotate the container.
So if you take, you can animate all these containers. You can do that. You can actually put transform data on any flip container and rotate it. I haven't tried it recently, and I don't think it'll work very well with receding, because receding really wants the boundaries to be orthogonal to the. It really wants the tank to be orthogonal. You can try that later on, or maybe I can do a separate file as a to-do on that afterwards to show you rotating a flip container, what it'll do, like rotating it on its end. Generally, it's not recommended. I think you can do it though. So the static object subsolver. Let's see if this actually works now. So object path. Use the same thing there. I just want to use collisions, collision guide. See if we actually get some collision guide data on that. If we go frame there. I might actually have to build some proper volumetric data, but let's take a look. No. So I might actually have to build the box as an actual volume. So let's go back to the box collider. And that should be easy to do. Just an extrude. Just put an extrude, poly extrude. Extrude right. And distance. And keep up back. There you go. So let's give it a little bit of thickness. And there you go. That should work just fine. And there's your collider. So then we can turn that on. Yeah, so, and that'll work. So that means that the box is now resized to work with the the flip container. If you change the flip container, the collision box will change with it. So, and that'll work just fine. He says. He says. It should be a static object. Square geometry. Collision guide. That's pretty fine. Yeah, that should work. If not, I'll fix it, but that's one way to do it. Okay, next question.
So you've shown a flip solver plus mode solver combo. You tried flip solver and flip, oh, the flip solver and flip solver combo, you would just need to use side-by-side values for both?
Let's take a look. What's the question here? You've shown a flip solver plus mode solver. Have you tried a flip solver combo? You could run two separate flip solvers. They won't know, the first wouldn't know what the second is doing, but you could absolutely, you could peer into the first flip solver to grab data into the second flip solver and vice versa. To be honest, that's what we're doing when we distribute flip solvers anyway. When we partition flip solver, we're really partitioning the source object multiple times. They are running into a single flip solver in that case, though. But when you distribute under the farm, you're essentially having flip solvers interact with each other through the boundary region, passing the pressure projection step and all of that. So you're getting that anyway. So yeah, you can use a flip solver peering into another flip solver's fields and work with it that way.
Jim says he wants the second and third question answered.
Oh, what's the second? Could you give one
The
example?
white water shell to create bubbles.
Oh yeah, okay, we can do that right now. So file.
On the ball.
So it's really easy. Flip tank. Let's just put down just a simple flat tank. And let's take the test geometry rubber toy, just drop it in. And I'm going to run it fairly coarse, and I'll show you how to basically do the bubbles. So we're really interested in just the, so let's go into the flip sim. I'm just going to make it a lot smaller actually. So initial, put it down. Just a nice small tank. And let's put down a ground plane. Got to move the ground plane down, or else we'll cut the fluid out, right? So, and let's take the rubber toy and turn it into a deforming geometry. And as I said before, it's not deforming, so turn it off. So I'll keep lay it out. Oh, that didn't work. So deforming geometry. There we go. That's better. And there's the test geometry, turn deforming off, and then press forward. So the white water should be getting some bubbles in it. So that's all we care about right now. So let's go to the white water import node and hide everything else. Press forward. That should ghost everything else, so you can see what's happening. And why is Clippy not falling down? I think I actually added this to the wrong solver. I added it to the wrong solver. That should be better. It should be falling down. Gravity. I'm being saved by errors now. Let's try it again. Oh, it's going to a static solver. Then to a rigid body solver. Static solver. That should be better. And static object. I'm going to add them properly again. Sorry about that. Step activity, deforming geometry. Let's forward. Nothing I'm doing today is work. So test geometries. Oh, I'm sorry. What am I talking about? I should be adding as an active rigid body object. Stupid me. And my brain's not working. So if I go test geometry, I have to blow away all those other geometry here, blow that away, because I got to add by the shelf tool. I just want to turn this into a rigid body object. Sorry about that. And then I want to go straight to the Wagner import, because I know it's going to work now. And there's definitely going to be some bubbles in here. If not, we'll certainly encourage it. And sure enough, on the bottom, there they are. So let's hide the objects. So these are our bubbles. And I'm just going to put down a blast. And add the angle. So I want to put the blast after the wrangler. And we just want to keep the bubbles. Should be a nice group for that. Bubbles. And then just show the p-scale. So I'm just going to do it right from here. So the idea here is to copy spheres. Merge them in. Or probably copy. Sorry about that. And they'll use the p-scale that's currently present. And if they're too big, then situate this a bit smaller, so you get your bubbles. And we're just going to use primitive spheres. I can turn these into packed primitives if I wanted to do instancing, but I'm going to put a null in here, and I'm going to put in here out of bubbles, because I want to merge it into my base surface is what I want to do. So there's my bubbles, and I'm going to move my display flag back into here. And in my base surface, which is the flood tank fluid, and so that's what I'm bringing in. Surface. So there's what I'm rendering. So what I want to do is I want to do an object merge of those bubbles into here, and bubbles into this object, and then just merge them together. First the water surface, and then the bubbles. And now hopefully we'll get some nice bubbles rendered in there. So let's add a camera.
People are reminding me to delete now, so I can have my
Oh, for God's sake. Those people would be very good. I'm sorry about that. So let me go back to that's under the Whitewater import. I actually was thinking that as I was playing with that. So that's better. I got a lot more bubbles. And there's my bubbles. Much better. Go up and let's turn Flippy off for now. Actually, let's do Flip on. Let's go to Cam 1. And I should have some good bubbles in there with the right off the bat. I should be getting something. So match with PBR. It's all out of skylight. And go to the render view. Cam 1 and hit render. And the bubbles should be in there now. But they're given a smoke shader because I'm rendering, hold on, I'm also rendering the Whitewater import, which actually is one of the fluid interior. Fluid interior could cause some issues as well. Let's knock that down a couple steps. But there's your bubbles in there once they render out. You can see them in there.
About 10 minutes. I'm going to move on to other questions.
Yeah, but there's your bubbles.
Okay, so the next question is a direction vector just a normalized work vector, or what is the difference?
It has everything to do with the transform nodes, the transform socks that we have. Depending on the type of normal, they get transformed differently. So what we can do in Vex is we can hint as to what that type of vector is, whether it's a surface normal, which is treated completely differently than a direction vector, which again is completely treated completely different than, let's say, a position or an orientation vector. So each of them have a different way of transforming. So basically, it's to support surface normals transforming on a surface differently than a direction normal would be deforming on that. So in Vex, you can hint as to what that vector is doing. So if you're using a transform VOC, for example, on a surface normal, yeah, you would have to say that this is a surface normal type. So that's where it becomes important.
The next question. Can you explain a bit more about collision weights and how to work with them?
Collision weights with respect to...
I think this was back at the...
Oh. Oh, oh, pardon me. Yeah, that's the field that's inside of Flip. I'm sorry. That field actually, if we open up that file, we can actually inspect that field. I don't think there is. Yeah, the bubble's looking nice, so let me stop that. File open. Actually, take a look at that file and see if we can play around with it a bit more. So that's in.
Then there were a couple other things around back to that example about why you didn't use fluid source internal curl noise.
Control. And just that you can, because you might not want to inject curl noise. You might want to put your own velocity fields in it or do whatever it is you want. If you have, let's say, an object or character that you want to impact the velocity field in there, that won't be supported off the shelf. So you're going to have to go in there and do your own special adjustments, right? Like add your own velocity fields in there, add your own velocities.
And then there was something else about why not multiply the curl noise by the pool that it's adding, and you don't need to switch.
Yes, that is a fantastic, yes, you can absolutely do that.
That's Mr. X-ray.
But the problem with that, though, is you're now you have the potential of mucking around with the other velocities that you just want to be uninhibited. And so that's why I'm using the hard conditions, because I really don't want to touch anything in Flip, because we could literally be processing, 50, 60 to 100 million points. So I want to have a hard condition in there that says do not do anything to these particles, because it's going to be overhead, unless there's a really hard condition. Whereas if you were keeping all the particles alive in there to do a condition against them, yeah, you could be processing, 500 million particles. So by using these hard conditions, you're tossing out most of them, and they're only working on that thin band. So with the conditions, for sure.
And then there was another comment about, isn't it better to use mu rather than two-way switch? If I remember correctly, two-way switch comes through and falls front, right?
Well, yeah, you can use an if you want, but I'm opening myself up with a two-way to be able to actually affect the base velocity as well. But you're right, you can use an if, because if you inspect the Vex code, the if will only do a single branch. You're absolutely right. It only does a single branch, whereas a two-way will do two branches, yeah.
And then another comment was, from my understanding, computing curl noise is most computationally heavy for computing built-in noises. So why compute this for a lot of points when it's not necessary?
Okay, so that's the big question: is curl noise worth the expense? Probably not when we're dealing with a fluid simulation. You could probably use any. Actually, we're going to come to this file in a minute. But I want to take up another one. The thing you get with curl noise is it truly is non-divergent, which means the noise that you sculpt essentially is the noise you're going to get out of the project non-divergence step within all of the fluid solvers. And that's why you would like to incur the expense of curl noise, because of its predictability, especially if you're passing this into the project non-divergent, as I said. Whereas if you just use regular Perlin noise or other types of noises, yes, they're faster to compute, but the problem is they will introduce pressure, either positive or negative, into the sim. So it's always just one extra little thing that might cause your fluid to boil up. And I'll show you a really quick example of that. I'm just thinking in my head, which is something that it'd be really easy to see that actually in play. So particle fluids. I'm just going to add a basic flat tank. And I'm going to inject curl noise and then Perlin noise into the tank, and then you'll see pretty quickly what's going on. Pretty straightforward. And I'm just going to run a very, very low resolution tank just so you can see this. So we're going to inject two different types of noises. So on the whitewater object, solver, I meant the white actually. I wanted to be I'm used to my layout. I actually I run an op script on the tool shop that lays them out differently. Sorry about that. So the flat tank, I'm going to run it like at a 0.3, so really, really coarse. Press forward, it'll settle right down. Not too much happening, right? It settles down, the particles are fairly straight. So I'm actually going to put down a pop 4-stop, and the pop 4-stop has curl in it, so I don't want to use that. I want to actually use pop. And wire that into, gas field, I'm sorry. So let's do a gas field. I remember this. And inside of here, we're just going to take not the density field, but we're going to take the velocity. And do the velocity. And we now know vector field. We don't have to look at the details view to know that this object has a vel field on it. And this time I'm going to do, it is a direction vector, so I'm definitely going to define it as such, or just a plain vector. And we're going to bring the velocity in. I'm going to put down a bind export, and this time it's going to work. Because my brain's working now. It's laughing at me. It's fine. And now we're going to inject two different types of noise. So we're going to put down a curl. And then we're going to put down just a regular under noise of regular curling. So just a regular anti-alias noise. And we'll switch between the two. So the curl noise is going to give you exactly what it is that you feed into it. A noise, I'm actually the 3D noise. 3D in, 3D out. And let's add that. Really gross, but it's going to prove the fact. And so we can also inspect the pressure field from the simulation to see where the pressure is being injected from the curl noise versus the anti-alias noise. And the position for both of them is going to be P, not the density. And then shift click on the sync. And so switch is going to be 0 first, and let's forward. So basically we're just boiling the fluid. But it's doing it in such a way that the pressure field should be almost 0. So if I go to the flat tank and I turn on the initial the guides, take a look at the pressure field. There's some pressure in there, but generally it's the pressure is mostly from the gravity. But if I go inside of here again and go to the anti-alias noise and switch to that, so switch input is 1. Go up again, press forward. Not strong enough either. So what's happening here is we're not getting what we put in. So what's happening? Why is the curl noise able to boil my fluid, yet the regular Perlin noise is basically just tickling my fluid, and it's got the same magnitude and same amplitude? And the answer is because the curl noise has no pressure artifacts, which means the project non-divergent step, and this is really important to know that the gas project non-divergent, let's actually put in divergent because I don't project. Variational is used inside of the flip solver. What it does is it takes the velocity field and it creates a velocity field. And it uses the surface field, surface weights, and a collision field. And that's pretty much it. So if you're feeding the velocity If you add curl noise to it, it's non-divergent. So that means this guy thinks that there's no pressure artifact, so it's going to let it pass right through. And that means you're going to get what you put in. Whereas if you start pumping in Perlin noise, this gas projectile divergence is going to wipe it out. It's going to say there's too many pressure artifacts, and guess what? They're gone. You might get some interesting swirls around the Perlin noise, but it's not going to get you very far. And as you can see very, very clearly, the Perlin noise, although it is kicking the fluid around, the pressure field has completely wiped it out. So it does give you some effect, but as I said before, it's most of its effect has been negated. Whereas if you go with the curl noise, you get exactly what you put in because it's got no pressure effects.
Might be a quick answer. What's the difference between a vector and a direction?
A vector is just it's a three position float that it just determines the directionality in space. It also determines magnitude as well. So from the origin, obviously. So as I said before, the type of vector that you define has nothing to do with the vector itself. All vectors have a 3 float. The difference is in how a transform operation works on those vectors. A surface normal, when you transfer a surface normal, it needs a different transformation than a direction vector, when you rotate a direction vector. So that's the really reason why you want to hint those vectors. That's all. It has nothing to do with the vector itself, and has everything to do with the operations that apply to those vectors. Hopefully that clears things up a bit. I sense something you need to do with vectors, but yeah. So next question.
Sometimes there are some little bugs with the BDB collider and static object. Once collided, some particles, instead of staying in the final place, it goes up and down. And if you've ever seen this, you know how to fix it.
So we took a look at the collision surface. We took a look at the surface field on Flip, right? So if I go up here, the Flip solver has, and I'll show you a more accurate way of solving those collisions. So under the flat tank, there is a collision surface field definition that's taken into consideration. If we go to the Flip solver, we go to volume motion, because if we're dealing with volumes, all colliders get converted into volumes, and then the Flip solver collides against those volumes. There's a collision tab in here. And this has a lot to do. So we're tuned for speed, for performance here. We're not tuned for accuracy per se. Well, as accurate as we can be within the solution itself. So we can actually go to the volume effects. We can change collision supersampling is the first thing I would try if I had a really well. First of all, I made sure that my colliders are well defined. This particularly in the previous webinar. I'll show you how to make sure that the collider is there and it's looking good. Then you can go straight to collision supersampling, samples per axis, to see if this will help solve those really tough conditions. As well, if you have a fast-moving collider, there's nothing like substeps to solve that problem, because I think we also talked about CFL and the predictor. You have to tell the solver that it's going to need the substep if it comes across some really high velocities, or else you won't know what to do with it. So next question.
I think this one is going back to the first example. Yeah. In the gas field Bob, in two-way switch, you add velocity to itself for particles for speed less than 2. Was that intentional?
Then that would be an error. The answer is no, you shouldn't be doing that. Yeah. If that's what I'm doing, I'll correct it.
All right. Next question. Can you also show how to make flip and bullet mutually interact?
They do mutually interact. And I've got a flat tank up here right now, so let's do this really quick. That is a straightforward option on the flip, and actually that gives us an example because somebody wanted to see the collision field inside a dot, so we'll do that as well. So we'll do that. I'm using an acronym that you're not supposed to use anymore. But kill 2 other creatures. But anyway, so that's going to go with the rubber toy.
No idea.
Kill 2 birds with one stone. Yeah, it's a so a metaphor. So basically, I'm going to this time actually turn it with a rich body object. Thank you, Dick. So so how do you make this guy float is the question. So if I go inside of the tank scene, lay out my network. On the flip solver itself, under the solver settings, it's the solver setting because we have to enable a feature. Hopefully, most of the time inside of DOPS, we're pretty consistent in that if there's a net new functionality that you want to turn on, if you need to initialize that data, it's going to be in the object that generates the simulation object into the simulation, or it's on the solver tab, and that's exactly where it is here. So feedback scale is what I need to increase. Yeah, it's not in collisions where you think it should be. It's in solver because, and of course, it's relative. We've got the pressure field. That's kind of neat. We'll see the pressure increase as the flip starts interacting with the fluid. But hopefully he'll start to float. I might have to increase it up a bit. He is interacting though. Yeah, so let me go to I'm going to turn off the collision. I'm going to leave the pressure field on. I'll turn that off temporarily. And I might actually have to increase the feedback scale to 10. You can go much higher than 10. And what this is doing is it's using that field that somebody asked a question about, which is, let's stop for a second here. If I go into the flat tank, there's a collision weights. So we can actually take a look at the do we actually have a visualizer for the collision weights field? I don't think we do. Collision velocity, we don't have a value of measuring for the collision weights. But hopefully I can show you how to take a look at that. Maybe call it a day after that. Yeah, so now he's being kicked around by the surface of the fluid now. I'm going to put a visualizer on it. But for that, you have to crack it open. I'm going to try not cracking it open and putting it in here, but I believe I have to actually find it. And see, there's Flippy's floating on top of the turbulent water now. And there is a center of gravity on Flippy himself, and that's a rigid body property. And you can take a look at Flippy, and that is actually being used, hopefully, by the flip solver to determine how he orients. But that's how you need to do it. So again, finding that it's a new property. So always take a look at the solver tab. If you can't find it in the other logical place, it's going to be in the solver tab. So that's where we dump the feedback scale. Now, as for the collision weights, we have a gas field box, so we can dive inside of there, and let's put down a bind. And bind, we're going to put down collision weights in here, and then no, the visualizer doesn't work like that. But first of all, we have the collision weights in here. But what I need to do is I know that the flip tank is defining the collision weight, so I can allow it into the contents. So this is an advanced thing, but it's really not that advanced. So if I dive inside of here, there's configure flip. So I'm going to, that's just the basic object. I'm seeing if we're actually building the data in here, and no, we're not. So it's going to be in here, so allow it into contents. And in here should be the node that defines and builds there's the collision weights data right there. Thankfully, it was named appropriately to the attribute that it's creating. Sometimes it's not, but in this case it is. Middle mouse is one of these things that you just got to use. Power users know this. I mean, they can go blind, put on any new node, and within 30 seconds they're using the node, because they know middle mouse gives them on the inputs, should give them objects to be on my map. It's not true, but data to attach. And so on this particular one, we can actually apply a visualization. So not visualization, scalar field visualization. So we have to know whether it's a scalar or a vector field, and this time it's a scalar field. So, oh, yes, I know. So scalar field visualization, and this is collision weights. I'm sorry, this is vector fields. Oh, it's a vector field. I'm sorry, I need a vector field. Vector field visualization. And then we can wire that in, and then we can visualize the vector field. Show guide geometry, bounding box. We don't want the bounding box, but we can use a plane, and then we can define the plane. This is generated in frame 1, so I have to go to frame 2. And there's my vector field visualization, and visualization type. Let's do value. Press forward. It's fairly low resolution, as you can see. But that's one way in that you can actually visualize the collision weights. So there you go.
Last question.
One more question?
How to make a tsunami? Is there any way to convert from soft to fluid? Why can't we have a shelf fluid?
Okay, collision weights in. Okay, so this will be the last question for today. How to make a tsunami have any way to convert from soft to fluid? I actually have some files where way back in the day prototyping how best to take a velocity field from a sculpted flip wave and pass it into flip. And that's fine. It does work. So you can actually sculpt the wave and give it some velocity. So those files, I can clean them up and put them out there and include them in this package if you want. I'll do that. But I have to say that in short order, they'll be obsoleted in the next release, because we have some really cool stuff coming within the next few months that actually does some pretty amazing stuff with sculpted waves as well. But in the meantime, if you need to get it done, I actually have some sculpted wave files. So you can actually create a tidal wave or a breaking wave and then run that into flip and let flip do what it has to do. So, yeah. And now you can actually do the standing wave, as I showed you. Actually, I should try that. Like doing a falling wave, because a breaking wave, one of the reasons it holds it up is all the air that it's packing. I should try seeing if I can do a breaking wave and pack some air in there as well with a velocity field. I don't know. I might try it. Okay.
Is there a quick way to suspend all clicks while navigating the timeline?
The only way to do it is auto update on mouse up. So that way I can scrub and then release it'll cook.
Okay.
On mouse up is what you want to do. Well, that's for changing parameters. On the timeline, you have to go manual, unfortunately. Manual and then press the reclick button.
There you go, Tobias.
Yeah, so.
I think that's it.
Yeah. So I've got all the files. They'll be fully documented. I'll hand off to Chris later on today. And there's a few more files in there that we didn't get a chance to touch on. But,
and questions.
Yeah, and I also have to clean up those files that everybody's been asking about. I got permission to distribute the Osprey as well. Just be reminded that it is side effects property, and if you want to use it in commercial purposes, you must contact us. But it's there for testing purposes for sure, and you can put it on Vimeo reels and stuff like that. So, yeah, so we'll clean up all those files for you guys as well. And that's it. Thank you.
Okay. Thanks, everybody. See you soon.